Log on, tune in, find out. Another good idea from Cambridge.
The next speaker is Alain Trouve, and he will talk on shape analysis of population of manifolds in computational anatomy.
Okay, thank you very much. Thank you very much also for the invitation and this to this interesting meeting and trying to mix different communities. So it's quite interesting challenge, in fact, to do that. So my talk will be some kind of follow-up of the talk of Laurent Younes yesterday, but for those who were not yesterday, so I will have some common parts at the beginning. So yes, this is some kind of second chance. I will stay in more or less in the same framework within the idea of using group action to define shape spaces, but I will try more to focus on trying to study population of manifolds rather than images. So I try to give some ideas about that. So I will just show some very few example of manifold you can have in neuroanatomy. So the first coming from a segmented structure in MRI images. So on the okay, this one. So here you have the 2D surface of the cortex. So you have fold. This is the 2D surface. Here you have segmented internal structure in the brain. So you have the hippocampuses here. You have many things. And here, for instance, you have. So this is, you can say this is also, it can be considered as a manifold or a collection of manifolds. You have, if I stay in the first example, if you look at the circle lines, which are the bottom of the folds, you have a bunch of one-dimensional lines. So you have this collection, and so you say this is quite jaggy in this situation, and so this is a collection. And here you have something which is more challenging. This is a fiber tracks you can get from DTI images. So here you have a lot of things like that. So is it a manifold? This is a collection of 1D manifold, for instance. This is kind of thing. So now imagine that you have a population of such shape. Can you do something with that? Can you try to start an analysis? So I will try to explain a little bit what Laurent said yesterday. So the context is to try to follow the idea of Greenender or to follow the idea of Darcy-Thompson, which is about when you want to study shapes. Maybe that's better to think about the transformation applying on the shape and to think about building distances on transformation and then on shape space. So the idea is that you start from, you have a group of transformation G, and you have a set of object M, and you have an action like this. So for any transformation G, for any object M, you have G dot M, which is, we can say, the deformation or the transformation of the object M with the action of G. So now I will assume that, in fact, M is a homogeneous space. I mean that I have a transitive action. I can single out a template, M0 template. And now I can define some kind of projection. So you have a mapping P from G to M, such that for any G, P of G is just the transformation of the template by the action of G. So I have this situation. I can say you have the G space here. You have the M, so upstairs, you have the M space here. So now, since this is an action for the identity is projecting on the template, M0. But since G is usually a very huge group, in fact, you have a lot of possible transformation projecting on the same point. So you have, as Laurent said yesterday, you have a fiber. In this situation of a group, this fiber is stabilizers or the isotropy group, the group of symmetry of the template, G0. Now, if I take another point outside this stabilizer G, I have a projection of G on another point M. I have again a bunch of transformation projecting on the same object. So this fiber is in fact G0. Okay, I can have another thing like that, projecting now in M prime. Okay, so in this situation, what I have is that I have a bijection between the quotient of this group with M. Okay, what I have not said is that I assume here that M is equal to GM0. So this is why this is a homogeneous space. I have a transitive action. So the idea is that now, if I know how to build a distance here on this group of transformation, not on this very complicated space maybe. This one is bigger, but it's simpler in sense. So if I can build a distance here, I can deduce a distance here by just saying that the distance between this and this will be the infimum distance between the two fibers. So if I have a distance dg, I will build a distance dm by just minimizing the distance between the fibers. But as Laurent said yesterday, in fact, if I want to get a distance here, I mean to have some equivariance property saying that, in fact, I mean that dg over G0, G1G is equal to dg over G0, G1 for any right multiplication by an element in the stabilizer of the template here. Okay, but the simplest setting is just to say that you have full invariance with respect to any G in any transformation in the group. So this is right invariance. So I will stay in this simple right invariant. So if I have right invariant distance on G, I can build any. I can project, and this is finally this is a Riemannian submersion. I can project any distance on the group on any different shape space on which I can act.
Could you just briefly tell us in the applications what is M, what is G, what is?
G will be in this application will be the group of diffeomorphisms. M can be a set of landmarks. N can be an image. M can be, we'll see, a current. M can be a lot of different things. And this is important. We have a lot of different possibilities for M. What is interesting is that, in fact, we will build a metric on M coming from just one metric on the transformation space. And for instance, this is something, if you have different way, for instance, you can try to approximate a line by landmark, and you increase the number of landmarks. But you want to have a Riemannian structure on the landmarks with n landmarks, n plus 1 landmarks, but you want to have something which is coherent between the different level approximation. In this, since they are coming from the same upstairs metric, you have all this consistency. So it's just not just trying to build a metric on a set of objects by just trying to find some fancy Riemannian metric, but it's coming from something which makes sense for the group, and after we have this projection. So there is some constraints, there is some limitation of that, and there is some good and bad aspect of that. Okay, as usual. So the good aspect is you have this consistency thing. So is that clear? Okay. Very good. Okay, sorry.
I have the same password.
So, okay, to build a right invariant metric on G, is that on a finite dimensional Lie group, that's quite easy, because you just have to define a metric on the Lie algebra, which is the tangent space at the identity, and by right translation, you build the metric everywhere. And after you use the geodesic distance. So this is completely standard. So we are not really interested in this finite dimensional setting, but more in infinite dimensional one. So that's a little bit more tricky in that situation. But there is a there is a way to do that. Is you start with a metric on the for the diffeomorphism, the tangent space has the identity. This is vector fields. So a metric on the vector field. This is a Hilbert structure. So you start with a space of vector field with a Hilbert structure. We will assume that this is a reproducible kernel Hilbert space. So it's you have a kernel somewhere, and the trick is that at the end, everything can be computing using the kernel you can design by yourself. So that's the trick at the end. So you have this vector space.
Vector spaces. What sort of metric on vector spaces do you use?
So on this vector space, the metric comes from a kernel. V is a vector space of vector fields. Okay? And I have a metric coming from a kernel. I have a kernel behind that. So
Well, that's one. That's not Hilbert, it will be one, right?
no, that will be Hilbert space. But I assume that I have an embedding. I have an embedding of V in the C1 vector fields here. Okay? So I assume that there is an for the construction there is an admissibility condition which says that I should control this. The norm on this V should be stronger enough to control.
So is this vector C01, you use H01 norm, right?
No. Here you use I'm assuming that you are using the supernode norm for you and the derivative.
That's one.
Yeah.
That's not Hilbert.
Yes, that's the Barr space. This one. Yes, but V is a Hilbert space. Yes. Okay. I understand your point now. So, what you will do, in fact, you will build all the transformation by just integrating time-dependent vector fields. So when you start for any V in L2, you can integrate the flow. So you integrate this equation. You have V this is a time. So for each time between 0 and 1, you have a vector field. You integrate the flow, and so you get all the solution for the finite for the V which are in this space. That means the kinetic energy is finite. So you integrate all of this, and you have a bunch of diffeomorphism, and this collection of diffeomorphism is a group. Okay, you can define a distance on this. So GV is defined by V. You have V and GV. V is not a Lie algebra, so there is some interesting question here. So you can define a distance, and this is the square of the distance. This is the infimum of the kinetic energy for if you want to compute the distance between the identity and the phi. This is the infimum of the kinetic energy for all the transformation for the identity to phi. This is a distance, and you can define a right invariant distance. This is exactly more or less the usual setting in finite dimension, but there is some interesting part here we have to do. And this group is quite nice because GV is complete for the distance, and you have existence of minimizing geodesic between any 2 points. So, but you have a huge choice for the metric on V. You just need to have this admissibility condition. So maybe I spent too much time on that. So now we have some nice way to build metric on this M space. So the idea is that to do statistical analysis, we can say that if you have a bunch of objects like this, you have a template, and you can use the exponential mapping coming from the Riemannian structure you have defined, Riemannian structure. So you can define what is exponential mapping. I mean, for any velocity field, you integrate the geodesic with constraint that the initial velocity is given by your choice. So you have a map from the tangent space to the M, and usually this is a local diffeomorphism in finite dimension. Okay, so in finite dimension, this is picture is more complex. So you have this geodesic equation, but this geodesic equation is not very, you have the Christoffel temple, it's not very usable like that. So the way we do it is different, so maybe I will skip that. There is a nice way to compute this the geodesic using the optimal control formulation. So Laurent said a little something about that yesterday, in a sense that now to define geodesic between M0 and M1, in fact you have a control variable at each time. You have a control variable which is a vector field, and you have the evolution m dot is equal to v dot m, and this is the infinitesimal action of the group of diffeomorphism on the object space. So to your question, Henry, and in fact this could be very different if m is landmark, if f is an image, if m is something different. You will have a different action, you have a different infinitesimal action. So you have very different situations here. But you have this, so it's this infinitesimal action come from just computing the derivative of p, in fact, at location p. So we have this, and we optimize this with endpoint condition. So we have a Hamiltonian system where you have here, you have a co-state variable, we call it the momentum, whose dimension is given by the dimension of the space, of this space, and not the dimension of G. It's much smaller. And you have here the cost, which is the cost appearing here. You have the cost which appears here. So this is a metric, the metric you have, and I introduce the L operator here. L is isometry between V and V star. This is a symmetric operator defining the scalar product with respect to the usual L product. You can see it like that. Okay, so and what we have is that in fact since we are looking for geodesic, we have using the maximum Pontryagin principle, we have this relation. We have the derivative of h with respect to the control is equal to 0, and this relation says something about v's, the velocity field you can have. It says that the velocity fields are defined by something which is called the momentum map, which is a function of m and p. What is the only message I want to say here is that the dimension of this object is parameterized by the dimension of p, and p is the dimension of the object space. But this belongs to the transformation space. So this is what we call the horizontality condition. Laurent mentioned it yesterday. It means when you want to lift a geodesic on the n space, you have a geodesic on the g space, but you have a horizontality condition, orthogonality condition, you can say. And this is here. So this is important. What I am saying that, just to say that this is important because it says that you can reduce, you have a reduction here which can be important for statistical purpose. Okay, so maybe I will skip this. And when we want to build a geodesic, we have just to integrate this Hamiltonian evolution. And you should know that in many situations this Hamiltonian is quite explicit, and this is not very difficult to do this shooting mechanism to integrate this Hamiltonian thing. So to compute geodesics is not something terrible. More or less, you just depend. It depends on the choice of L or on the choice of the inverse K, which is defined by a kernel. So I do not want to show explicit formulas, but you have some quite simple things. Okay, so if you want to build mean and lattice, what can you do? You have this, so you can define Cachan means. This is a usual way to define this. So using the minimizing the square of the distances in M, we know that there is problem of existence at uniqueness depending on the curvature of the space. So I think that Mario will say a lot about that curvature tomorrow. Yeah? So you have a special lecture tomorrow for about this curvature question for landmark cases, which are quite nasty and difficult, but Mario has some very nice result about that. So, but this is standard way we can minimize by just using this Riemannian structure. We can do what usually people try to do with doing statistics on Riemannian manifold. In that setting, so usually I should say that usually what we are observing, M is some kind of, say, model space. But usually you can have observation, we can be noises that's some kind of what is living here, because don't forget that the model space is the orbit of the template under the action of the deformation. So it could be, this is not everything. And so usually what you have, the observation space is larger. So you need to introduce some kind of distances, this discrepancy here between the observation and some kind of estimated point in the mole space, like this. So you can imagine. So you have also other things here, like this. So
Your M is embedded in something larger.
M, this is M.
In something larger.
And you can say you have a Y, which is bigger somewhere. Or we can live elsewhere. So in some situation, I will show you a situation for manifold. So in some situation, you need to have some discrepancy here to say how high I can. You cannot avoid that. If you go up, if you stay inside the geometrical framework, everything is clear. But on the real situation, you need to have this kind of thing. Plus this thing. Now you can lift everything on the group and say what you have. If you want to find the mean, you have to minimize in M0 here and minimize on a set of deformation and the sum of the square of the distances, because we know the connection between distances in the group and distances in the manifold, so I can go from dm to dj, plus this, and mi is just is a point in the orbit. This is a deformation of the template biases. Okay? So I can do it. But you know, I need to have, for instance, these kind of things. Okay, so I'm quite late. So, if I want to, so we can act on points, we can act on images, we can act on many things, but we can displace manifold. But if I want to do this for real, there is a challenging problem for some manifold data, is that a manifold is not just a surface. It's something which is independent on any specific parameterization. You have a chart and you have equivalent parameterization. So the manifold is just the differential structure on the surface is not a parameterization. So it does not depend. As a manifold, this is not just a matching function. This is matching surfaces. It does not depend on any particular parameterization. And if I look at noisy observation of manifold, because in segmented data you have a lot of noise usually, and for instance, fiber track you have interruption, you have many bad things. You have that observation can be something which is not a smooth manifold or a manifold at all. So we have to think about that problem. So the idea is to use mathematical currents. I think it goes by this idea of currents. Mathematical currents goes by to the RAM, but it has been introduced in this setting by Johan Glonès and Marc Vaillant. It has been quite an important breakthrough to really work with in this setting with manifold. So what is the idea? So current is, in one word, current is something which can integrate differential form. So if I denote omega PRD, the set of continuous P forms, so have a dimension. Now I have to P will be the dimension of the manifold at the end. So if I look at omega P form, we know that we can integrate P form on a manifold. There is a standard way to do that. And if you work with coordinates, in fact you can, if you have a chart or local chart on this manifold u gamma to u to x, this is computing like that. So you integrate over the parameter set of omega at position gamma of s of this. This is a p vector, and this is a p vector which is generated by the partial derivative, directional derivative of gamma with respect to the different parameters. And so, in fact, we know that this expression is not depending on any particular parameterization. I mean, if I have another parameterization psi, and if I look at gamma composite psi, which is another parameterization on the same manifold, in fact, you can compute this. This is the magic of exterior product. This thing is exactly the previous one with the Jacobian here, and so by a change of variable, you show that this is the same thing. So this is intrinsic. In fact, it does not depend on any parameterization. So X can be seen as an element of this dual space, and the dual space, this is a space of current. So the dual space of the P form. So important thing is that it depends on the orientation, because this, you know, in this change of parameterization, that's okay if the Jacobian is positive if you preserve orientation. So it depends on the orientation. Okay. So the idea is that we have this space of current, which is something you can see manifold as a current, but this is a much bigger space, and this is a vector space. But since we would like to do statistics and we would like to do analysis, we would like to have some norm, and hopefully we prefer to have some Hilbert norm on this. So the idea is very simple. So if W is a RKHS, a reproducible kernel Hilbert space on the space of P form, and it's a dense subset of continuous P form, vanishing 0 is to vanishing at the identity, then in fact, looking at the dual, you have the dual space is embedded in W star, the dual of W. And on W star, you have the dual norm. And it happens that when you know this kind of thing, the dual norms, if you define W with a kernel, in fact, the dual norm is very easy to compute with a kernel. That's the trick. So in fact, we can embed this space of current into W star where we have a Hilbert structure. And we can compute, in fact, using the kernel, we have a nice formula to compute the scalar product between any two. I have two manifolds, and I want to compute the scalar product between the two currents associated with that manifold. And I have, given the kernel, I have a nice way to compute this. Okay, but this is, in fact, this is a continuous integration. So this is not very practical in that step, but theoretically, I have this structure. So now I can add, I have the possibility to add things, to make averages, so that could be interesting. So an important tool is to speak about punctual currents and approximation. So in the space of, I know that a manifold is a current, but there is very simple things which are currents, which is we call it a punctual current. What is a punctual current? This is some kind of infinitesimal manifold, in a sense. So you take psi, which is a p vector. So just a key element to understand for people which are not familiar with p vector. I was not familiar with p vector when I started. So if you have V1 Vp, if I say that this object, what is this object? What is coded by this object? Psi is coding, in fact, psi is equivalent, it's coding what? It's coding the span of the Vi. It's coding an orientation, which is a sign. And it's coding also, it's coding a surface. So we can rely on your intuition for the two-dimensional setting, but I do not want to, I prefer to stay in this general setting because there is some misleading conclusion here. So, and you have another thing which is the volume of the domain, which is defined by the V1, V2, V3. Okay, so this is a determinant, this sign, so you have a volume, a p-dimensional volume. Okay, so I can say that d delta xc is some kind of, you have a location c, you have a location x, you have a psi variable which could code some kind of say subspace. And this is a current, and as a current, it should be linear form on omega. And so I have that. If I apply it on the p form, I have this. This is evaluation. So this is evaluation of omega at x under the action on psi. Okay. So this is an atom. This is a very simple thing. I can say this is just an infinitesimal representation of that. So in fact, I can discretize any manifold using this representation. So for one dimension, if you have a line, in fact, a nice way is to say you discretize. You don't need to have regular discretization. You need to have discretization enough. and you replace this segment by just xi will be the difference between these two things, gamma s plus 1 minus gamma s, times something located at the middle. And if you refine, you have nice approximation stuff saying that for the dual norm, you will converge to this. For triangulated surface, that's more or less the same thing. In that situation, you have an isometry between two vector and normal vector because 3 minus 2 equal 1. So that's why we are lucky in 3 dimensions. This trick does not hold anymore in more general situation. But you have this, so you can represent punctual current like this. But this makes sense for arbitrary dimensions. So for 2-dimensional surface in 4-dimensional space, that makes sense. So also we can, for instance, if you want to approximate a manifold by a sum of punctual currents, there is a nice way. Since we have the Hilbertian structure, you can use some kind of matching pursuit algorithm to do that. So there is a nice way using, and everything is explicit because when we work with punctual currents, the most what we have is that the elementary as you say, the 6 kx1. Okay, you have elementary, you have explicit formulation of this elementary scalar product by just using the kernel. So everything can be done quite easily. Okay, so now if I want to use this current and if I want to connect with the previous framework, I have my discrepancy here, which can be defined as the dual norm for current, or maybe a function of this dual norm for current, because current is something which is really intrinsic, is associated to the manifold, not to the parametrization. This is an important point. So we can define this, and so later I use h equal x squared. So if I want to find, for instance, the mean, I can solve this problem. So I am minimizing C0 and phi1 phi n of this. And here you have the discrepancy, which is the square of the dual norm. And here you have the action. You have an action of current. And something which is important, I have not mentioned yet, is that there is a natural action of P form of diffeomorphism by pullback, and there is a dual action, which is a push forward of current, which is completely defined, even for very nasty current, because it's well defined for the P form, and so by duality it's defined for current. So you have a nice action here on current, and that's very easy to explicit what's happening when you have. Yes?
I'm wondering how about the uniqueness of this current representation?
No, you have not uniqueness usually.
I mean, is it possible 2 different manifolds you have the same current?
Oh, yeah. Okay, that's a question. Yes. Yes. No. In fact, for any manifold you have just one current.
But I mean,
Yes. You have injectivity. You have injectivity of this. Okay. You have two smooth manifolds. No, you have injectivity. There is no. This is really this is much richer. In fact, you have manifold, but you have more of the things. So. Okay, so we can do this kind of thing, and this has been done in the PhD thesis of Stanley Durleman. I will mention it at the end as a reference for people, because we'll be interested to look more carefully inside this. So I show you a simple example. So here you have fiber tracks, and you have 6 subjects. And we like to try to just to have a look on this population, for instance. So here, this is a current. This can be, this is a current. This is a bunch of lines, and this is well defined as a current. Yes, you have these fibers, and you can do this approximation. You can use projection pursuit if you want to control the complexity of the representation. And so what we get here, for instance, this is one subject, and this is what we get, the average. The average, which is represented as a sum of punctual currents here. So it looks like a simplified thing, but this is for the current norm. This is a good approximation of the mean. So here, so this is a template, and you have two different views for the sixth subject. So we can do statistics. So I will try to not to stay too long on this, because you can believe, you can guess what I want to say. So when you have your population, you compute your deformation, and what you get, you know that your deformation is, in fact, is. So to answer again to your question, so for current here, you can say this could be a collection of punctual currents. So it can be a finite dimensional space here. So when you have your mean, which is in fact a sum of big number of punctual counts, and this is something which is finite dimensional. So you match to all the example. You get a geodesic. We know that we have a constraint on the geodesic, and the geodesic, the initial velocity field is controlled by a parameter which is in fact the momenta at time zero, p1, pn, and this momenta is finite dimensional. Okay, so we have a collection. This is the initial direction, and you can try to do your the kind of statistic you like. So you can do PCA. We have done PCA like this. You can do much more fancy statistic if you want, but okay, you have an analysis of this deformation. So we did it for the sucker lines. So in this situation, we have a bunch of brain given by Paul Thompson, in fact, and we have a bunch of sucker lines, and we have the matching to all the sucker lines. We do this deformation analysis, and since we have global deformation, if you want, we can look at the deformation not just on the sucker lines, but on the cortex itself. So here, this is the first mode, and so we have some deformations. So we go 1 sigma in one direction, 1 sigma in the other direction. This is the mean cortex, and we have different deformation here. Okay, so this is based on pairwise registration, because here. Maybe I will go to this one, because this is less conventional. So this is for fiber tracks. So for fiber track, what we get a bunch of deformation. When we have computed the mean, we have a bunch of deformation, and we have a bunch of residues. But residues are living in this dual space. So we can try to say, in fact, so this is a difference of manifold computed as a residues, as a difference between currents. And we can try also to analyze this. Could be interesting. So we try to do this. So we can have a joint analysis. I cannot say that we did the best, but we can try to think about the joint analysis of this deformation of this residue. Here, what we get, this is a subpart. This is not all the tracks, the fiber tracks. It's one of these fiber tracks. This Corti, don't ask me what. Okay, this is here. So here we have. This is the mean, and we have this is maybe I can show you this. The first mode. Oh no. Okay. Okay, maybe I have to say okay. Okay, so it's working. I don't know. Maybe this is with the. I tested several times, so I don't know. Maybe this is behind the slide. Oh. My God. I did the wrong thing. Yep. Okay, so the video. I will show I promise I will show the video for after my talk for people. The video is quite interesting. So for the first mode, you will see the deformation, but you can so because here we cannot. This is 3D, so here we have some problem of perspective. So we see that we have really something which is this is just transport of the punctual currents, but you can do also the same for the residue, and we can see that we have evolution in the situation. What you can see, we have difference of symmetry, the density of fiber between the left and the right. This is more or less what we get on first mode. So this is a kind of idea we can is the kind of thing we can do. So I have very few time. So I would like to say something about generalization of this approach. So I will say a few words about that. So in fact, there is an interesting situation where you have not only shapes or like fiber tracks, but you have a shape with a signal on it. So in fMRI, for instance, but okay, we show 3 different things. So this work has been done by with Nicolas Charon, which is currently a PhD thesis in my lab. So PhD student in my lab. So you have here an example. You have this shape and you have a signal. So this is don't try to make any sense to this. This is not blood on the finger. This is just signal. Don't worry. So we have this. You can say you have a manifold with a vector field on it. You have manifold with a tangent field. So usually you have simultaneously you have different things. You can say statistically it's interesting to say, okay, what we can do when you have manifold with signal on it. So you have information in the shape of the manifold and information in the signal. So can we try to work with that? So we are not the first one to think about. So I say I can think about something which is a manifold plus a signal. F from X to S. S is a signal space. So I have a field of signal here on the manifold. So this I call a functional shape of this. Okay. It's not the best name, but this is the name. So 3 examples of this kind of thing. So can we work with that in the same? We can imagine some way to act on this kind of object by diffeomorphism. You can understand. You can propose different things, but now can we work in that setting with the same classical current? So in fact, the answer seems to be yes if the signal is a scalar value, and because we can for any pair x f, x is a manifold, f is a signal, we can build a current which is associated with this by just integrating omega on x, but using a weighting factor f. Okay, and so this defining current, and this is uniquely defining this pair, in fact. So if you look at this approximation by punctual current, what we can say the approximation is something like this. So we recognize the punctual current, but we have weight here. But there is something which is there is a drawback in this. The first one is that we can just do this with real-valued signal. We cannot use it in a real situation. And another thing is that we mixed here in this punctual decomposition, which play a very tremendous role in all the numerics. We mix the geometry with the signal. Okay, this is very simple because if you multiply by r this, you can put the r inside the psi. It means you can pass the signal into the surface and reciprocally. So there is something which is ambiguous in this decomposition. So in fact, you cannot really do that. So what we propose and what we are currently studying, so this is very recent work here, is to work with what we call functional p-form. So functional p-form is, okay, it's our nickname. I don't know if this is mathematically a very good name. I don't think so, but okay. Say, at least for this talk, I will call a functional p-form, which is something which is a continuous thing. For each point on the space and on the signal space, I define in fact a linear form on the p vectors. So if you have to just to remember that this, so the space of continuous p form is just this. So what we do here is we do a product here. Now, here, product here. So, and we define the functional current as the dual space of this. Same trick. So I should say that functional space are not current in this product space. It will, okay, it could be the first idea, but in fact it's not a good idea to do this. And we can also have punctual things in the same way, Dirac F current, punctual F current, which are defined in this way. So here you have still this psi, which represents some kind of orientation, and we have this. Now we have a delta measure, which is on both the location and the signal. Okay. So I will. I'm running out of time. So I will say maybe I will show you two or three slides, and I will end. So in fact, on that space, there is a natural way to define a dual norm again. So more or less, you can see that F current is a product of two things. So you have a part which is a geometry and the part which is a signal, and you have this product measure can be used to define a kernel on that space. And so what you can just the message I want to say is that in fact you can use two different kernels, one for the geometry, one for the signal, with two different scales, characteristic scale. Sigma f for the signal, sigma g for the geometry, and in fact, depending on that scale, you can look at your functional shape as just a pure geometric object, or as a pure signal object, or as a mixture of them. So you have different scales. You can play with that. We don't really know for the moment how to play really correctly with that, but we know that we can do it. So for instance, when the geometric scale is going to infinity, you just see your functional shape as a bag of signal, as a mirror of signal. You have no more. You don't know where the signal. You just know the collection as a bag of features, a bag of signal. And so we have some primary result on that. Just to understand this new norm, what is interesting is that if you have the same manifold, but you change the signal, this dual norm is upper bounded by an integral over the manifold of the geodesic distance between the signals. We assume that S is a remaining manifold in that situation. So it means that in this representation, when you have the same manifold, but you have a sequence of signal which, with pointwise convergence, you have the pointwise convergence of the dual norm, and that's important for the robustness. We have more. We have another analysis here with where you have your functional shape, but you deform the shape and you deform the signal simultaneously, and you want to see if you have continuous to this deformation in geometry and the signal. So we have a result more or less saying that we have a continuity for a nice this is a classical norm for this kind of deformation. So I have to stop. So that's my last slide. So I have no time to go further on this, but we are actively working on this kind of framework. So we see that this is quite general situation. We have quite flexibility with the parameter sigma g and sigma f. We do not mix signal or geometry, or we know how to mix it. We don't need to have point-to-point correspondence between the different things. So the idea is not to first to have a mapping first of x, of the different x to the same shape, and after to pull back the signal, and after to do in a second step to work the signal, but to do things simultaneously. Okay. Just to show some new funny pictures, but in fact this is projection pursuit in that setting. I have no time to explain. So, few references, and thank you for your attention.
Thank you very much. Maybe we have time for one quick question. If it's not the case, so then thank you again.